Welcome to this week's Frequently Asked Friday. Today the question is, how to determine sample size for a clinical investigation? A short and simple question. However, unfortunately, a short answer is impossible. Sample size determination depends on the type of study you plan to conduct, the power and significance level you pursue, and several variables about the expected result. These may be known, but more often they must be guessed or assumed to the best of your knowledge, supported by literature and guidelines. Probably the easiest study design to calculate the sample size for is a study in which two therapies or methods are compared with a simple unpaired t-test. This means a group that receives the treatment under investigation compared to a group receiving a standard of care, an equivalent treatment, or, if this is ethically appropriate, no treatment at all. To be able to compare groups with a t-test, the primary endpoint must be continuous and normally distributed. For the sample size calculation, the mean and standard deviation of both samples are needed. Here the assumptions get into the picture. For the control group, literature is your main source. Literature will also help to determine which endpoint is common in the field. If it seems impossible to find a mean and standard deviation in literature for the control group, the primary endpoint might be too uncommon, and this could be a reason to redefine the primary endpoint. If you do find enough studies investigating the control treatment, this literature is probably reporting a range of means and standard deviations on the treatment's performance. Now this should be bundled into one number to feed into the sample size calculation. A recent review with the meta-analysis would be super useful at this point, but usually unavailable. The next best thing would be a recent randomized controlled trial, or RCT. However, this is probably also unavailable. Hopefully, the literature is in consensus and an average of reported ranges can be used. Otherwise, choices should be made. Appraise the available data carefully and choose the mean and standard deviation obtained in settings and with techniques most like the planned study. As the true standard deviation is almost always unknown, it is sometimes worthwhile to estimate the upper bound on the observed standard deviations and use that for estimating the sample size. For the treatment, a pilot may have been done to provide the mean and standard deviation. However, this may also be estimated based on the literature. A slightly different technique may be available that may provide the mean and an indication for a standard deviation, which can be used for the sample size calculation. Another option is to use the desired mean of the new treatment. The standard deviation of the control treatment can be assumed for the treatment group 2. A little background on a t-test. The t-test eventually provides how likely it is that the compared groups are equal. Now look at these curves of normal distributions. If the curves overlap considerably, it's easy to conclude that the treatments are equal. On the other hand, completely separate curves clearly show a difference. However, in case the curves overlap, statistics are needed. The t-test compares the means of two groups to the hypothesis that there is no difference and will determine this with a certainty of commonly 95%. Or a different percentage if another alpha or type 1 error is chosen. Commonly, our aim is to show a difference, hence to have curves overlap as little as possible. By increasing the sample size, the standard deviation decreases while the mean remains unchanged. In the picture, this would equal a higher and smaller curve. Hence, they are easier to separate. Depending on what should be proven, equality, equivalence, non-inferiority or superiority, the sample size may further increase, where non-inferiority commonly needs the smallest sample and equality the largest. Notice that the distribution of the means should come from a normal population, and that it should only be reasonable to assume that the sample comes from a normally distributed population, while the sample itself can diverge from a true normal distribution. If the diversion of the sample from normal is too large to argue that it originates from a normally distributed population, a non-parametric test should be used instead. The non-parametric equivalent of the t-test would be the Mann-Whitney U-test. The final test is always performed on the collected data. If the means and standard deviations differ from the assumptions, the test is unaffected. If the test provides a highly significant or non-significant conclusion, the sample size apparently was large enough. However, if a borderline non-significant result is obtained, the sample size may have been too small to detect the difference. In that case, a power check could be performed. That means that with the current means and standard deviations, the current power is calculated. The higher the power, the higher the chance that the observed result is the actual situation and the treatments are equal. A power below, as a rule of thumb, 70% suggests that the study is underpowered, and the larger sample size would be needed to be able to definitely conclude if there is a difference. This is the reason why a sample size calculation should aim for sufficient power, as insufficient power could mean a waste of resources. The sample size of a study is calculated for the primary endpoints only. If you have several, the calculation is made for each and the highest number is usually taken, sometimes with an additional surplus to be able to correct for multiple testing or loss to follow-up over the course of your study. Obviously, much more study designs exist than a study with two independent samples with a continuous primary endpoint. For your specific situation, QSurf can always help with your sample size calculation or assist in finding numbers for the required assumptions.